Welcome to The Explainer. Today, we're jumping into a huge problem for anyone working with large language models. How in the world do you get those massive, super powerful models to actually run on hardware that you and I can get our hands on?
All right, let's dive into a scenario that, well, it might feel a little too familiar for some of you out there.
So picture this. You've done it. You've trained or fine-tuned this incredible state-of-the-art model. It's brilliant, it's powerful, and it's a whopping 51 gigabytes. You're ready to go. You're ready to deploy this thing and show it to the world. But bam, you immediately slam into a hard physical wall. Yep, your hardware, the very GPU you need to run it, only has 24 gigs of video RAM. So what happens? Your brilliant AI just doesn't fit. It becomes a very, very expensive digital paperweight. So how do we fix this? How do we solve this puzzle? Well, the answer is this absolutely brilliant technique that's become pretty much essential for anyone doing AI in production. It's called quantization. And honestly, this is the best way to wrap your head around it. We're essentially making the model files smaller, just like you take a massive 50 megabyte raw photo and turn it into a perfectly good 5 megabyte JPEG. Do you lose a tiny, tiny bit of imperceptible detail? Yeah, maybe. But the important thing is, now it actually fits. So what's really going on under the hood is we're making a deliberate trade-off. We're giving up just a little bit of numerical precision in the model's brain, you could say, for these huge wins in memory and speed. And, when you do it right, that little dip in quality is almost impossible to notice. Okay, so let's talk about when this all happens in a model's lifecycle, because there are really two main ways to go about it. But as you're about to see, one of them is way, way more common for just about everyone doing practical work. Right, this slide lays it out perfectly. On the left, you've got quantization-aware training, or QAT. Think of this as the super complex, do-it-from-scratch method that the big research labs use when they're building a foundation model from the ground up. But for the rest of us, for anyone taking a model that already exists and wants to actually use it, we're looking at the right side, post-training quantization, or PTQ. It's way simpler, way faster, and it's what pretty much everyone does. So that's exactly what we're going to focus on. So, with our focus squarely on PTQ, let's get practical. Let's walk through the actual actionable playbook for getting this done. Look, if you just want the get-it-done recipe that works in most situations without getting totally lost in the weeds, this is it. This is your go-to. Use the AWQ method. Aim for 4-bit precision and, this is important, calibrate it with a few hundred examples of your real-world data. We're about to break down exactly what all that means. The whole process can really be boiled down to these 4 logical steps. It's a nice, clean flow. First, you decide how you're going to compress it. Then you feed it the right data to learn from. You set the level of compression you need. And finally, the most important part, you check to make sure it all worked. And for that first step, choosing your method, here are your big 3. Think of it this way. Deploying on a big server with powerful GPUs, start with AWQ. It's modern and does a great job protecting quality. Running it on your own machine, like a MacBook or a CPU, GGUF is your best friend there. And GPTQ? That's your solid, super reliable backup if you hit any snags. All right, next up, you've got to ask yourself just how much compression do we really need? This is where you decide exactly how small to make the numbers inside your model. And wow, the impact here is just dramatic. Moving from full precision down to 8-bit cuts your model size in half. But the real magic, the sweet spot for most things right now, is W4A16. That gives you an incredible 75% size reduction. That is massive. The W4 means 4-bit weights, but that A16 part is super important. It means the math, the actual calculations, still happen with 16-bit precision, which is the key to keeping the model's quality high. Okay, so you've run the process. Your model is smaller. But here's the million-dollar question. Did it actually work? This is, without a doubt, the most critical step. How do you know for sure that you didn't just create a smaller, dumber model? You've got to check it against these 4 pillars of success. 1, does it actually fit? Check. 2, is it faster? What's your real-world speed? 3, is it still smart? Did you keep the quality? And finally, 4, is it stable? Because let's be honest, a model that crashes all the time is totally useless, no matter how tiny it is. Okay, let's tie all of these pieces together. We can actually build a really simple, step-by-step decision framework you can use every single time you do this. So here it is, your cheat sheet. Step 1. Do you even need it? If it doesn't fit, yep. Step 2. When are you doing it? You're deploying, so that means PTQ. Step 3. Which method? Easy. AWQ for servers, GGUF for your laptop. And step 4. How much? Default to low 4A16. See? It's a really clear path that'll work for like 95% of use cases.
At the end of the day, this is so much more than just a clever technical hack. Quantization is what makes modern AI practical. It's the bridge that takes these incredible, massive models out of the research lab and puts them into the real world where they can actually help people.
By knocking down those hardware walls, you can finally stop worrying about the limitations and start focusing on innovation. The goal isn't just to shrink a file, it's to unleash the intelligence you worked so hard to create. So now that your model fits, and it's fast, the only real question left is, what are you going to build with it?